Okay, welcome back. Let's continue. We talked about functions last time. We're ready for this new concept called relations. So let's get into them. What in the world is a relation? Well, it's meant to model a relationship between two sets. So that's the quick answer. Let's formalize how we can define a relationship between two sets. Okay, let's do that. Okay, so again, let me draw two sets, because I'm first going to give you a binary relation definition. That's the most common form of relations. So here's x and y again. We can have them be the same as last time, like x can have 3 elements, y can have 4 elements. Totally fine. And here's x1, x2, x3. Here's y1, y2, y3, y4. We can do this. A binary relation between two sets A and B is a subset of A cross B. So this is very similar to the definition of a function, but we can have a much more relaxed definition. We don't have to have as many requirements. We just want to be able to express the idea like x1 and y1 are related in some way, let's say. x1 and y1 are related, they're brothers, and maybe x1 and y3 are also related, like they're cousins or something. You can have multiple things emanating from the same x value. Oh man, crazy. And this is the relation R that's talking about them. And maybe x2 is related to y2, but like x3 is an only child, so it's not related to anybody. That's totally fine as far as relationships go, right? We're just using sets to model relationships. And so that's already quite different from a function. Do you see that? So again, it's just a subset of A cross B pairs. So we can define a relation to be just like, okay, what's related? x1 is related to y1 in some way, x1 is also related to y3 in some way, and x2 is related to y2. These represent our relationships, okay? And again, it looks very similar to a function definition, but we don't have to fulfill any more requirements. You see that? So, yeah, if you have A comma B in R, in that relation set, then that means that A is supposed to be related to B. We'll also write this, instead of saying it like this, we'll shorten it to say ARB is true. So like x1 is related under the relation R to y1, for example. x1 also is related to y3, so I could also say x1R y3. So putting it in the middle like that is going to make sense soon, I promise, for relations that we already know about. All right, so here is an example relation. Let's say that the relation T is defined this way. Two elements are related under T, where x is the first thing and y is the second thing, if this is true, where x is in Z and y is in R. All right, so xty is true if x is equal to the floor of y plus 0.5. Interesting definition. Let's see what some numbers are that are related under T. So for example, 3, the number 3 is related under T to any real number such that that real number plus 0.5 floored is equal to that original number 3, original number x. So 3.14 is related under T to 3. Similarly, 6 is related under T to 5.67. Because if you add 0.5 to that, it's 6 point something. Take the floor, it's 6. That is the round relation, the normal mathematical rounding relation. This rounds to this. See that? This rounds to this, either up or down. And you can define it in terms of floor, surprisingly. Crazy. So relationships are very, very necessary to be able to express in math, don't you think? So you can draw pictures like this. That's totally fine. You can also make a matrix form of a relation. Okay, so let's draw a picture of a relation between finite sets, not using a bunch of ovals and arrows, but using a matrix. That's the more standard way of representing these things. So we can make a matrix representation of a relation between two sets A and B. It's just, well, you draw a matrix It's a 2D array of numbers with, and usually we put the first set as the rows, so A is on the rows, and the other set, B, the thing that's being related to by A, is on the columns. Okay? So, yeah. A1 in row R and column C means that AR and BC are related. So you can write either ones or zeros in your matrix, true and false. Like, these things are related if it's a 1, and they're not related if it's a 0. So for example, here is my relation C, let's call it. P is related by C to O if person P has object O, right? So here are people. I am a people, and let's pretend that NASA is a people too. So 2 people in our universe. And here are some objects that those people might own: a car, a cat, and a spaceship. Okay? So for me, for example, I own a car. So match those up, and there is a 1 next to that. Lawton and car are related under this ownership relation. I also own a cat. So there's a 1 there. And I unfortunately do not own a spaceship right now. If you know somebody who can give me a good deal, I'd be happy to change this. But for now, I don't have a spaceship. And okay, let's talk about NASA now. They definitely have a bunch of cars for their people to ride around in, to their spaceships, right? Because they also own a lot of those. But I'm pretty sure NASA is not doing any experiments on cats anymore, if they ever did. And so I think that they are not related under this relation of ownership. Okay? So here's our relation. Lawton is related to car, Lawton's related to cat, NASA is related to car, and NASA is related to spaceship. This is the matrix form of that. That's all. Okay? So the first thing, the left side of the relation is on the rows, and the right side of the thing is on the columns. That's not too bad, I hope. Okay, so you can represent a matrix as a relation, and that's that. Let's talk about binary relations on the same set, because that is a very, very common thing to have. You can relate elements of one set to that same set, maybe other elements of that same set. Okay? If you have a binary relation like this, where A's are related to other A's, maybe the same A's even, that set A, because there's only one set involved right now, that's called the domain of the relation. Okay? So, similar to function terminology, but different. Okay? So, yeah, let's talk about all this stuff. So, you can have relationships between elements of the same set to itself. So let's pretend we have some real numbers. Let's have a binary relation on the real numbers, where R is the domain of this binary relation. We're taking elements to potentially other elements in R. Okay? So the first thing that I want to talk about, the thing that can appear, is self-loops. Elements can be related to themselves under a relation, right? Self-loops are possible when you have the same set twice, when you're relating the set to itself. So elements can be related to themselves now. x1 can be related to x1. You can also have this, like x2 can be related to x3, and x3 can also be related to x2, like they share things in common. That's totally fine. You actually know a ton of binary relations already. On R, in fact. Look at all these. These are just relations. And now you know why why people write them like this, because we're just copying these original relationships that existed before like this fancy notation got invented. So this is just a subset of R cross R, is it not? The less than relation. 2, 3 is in the less than relation, now that we know how to pronounce this, right? All that means is, yeah, 2 is less than 3. You see that? Isn't that cute? So, same with these guys. Greater than or equal to. Again, a relationship, a binary relation on R, for example. It doesn't have to be on just R, though. You can constrain this to be only working on natural numbers. Like, I only want to talk about greater than or equal to for natural numbers right now. Or I only want to talk about equality for integers right now. That's totally fine. You can specify those things. And so now we can talk about like what it means to be greater than or equal to in natural number land. Like 5, 2 is related under the greater than or equal to relationship, right? Because 5, which is a natural number, is greater than or equal to 2, which is a natural number. That's a relationship. It's true or false answer. You see that? Isn't that neat? And so finally for this one, like -2 is related to -2 under the equality relation. Yeah? All that means is -2 is equal to -2. See how we are used to writing the relation symbol in the middle? Now we have it. Let's write a better equality. Okay, so now I hope you see why this notation makes a lot of sense, and that relations aren't scary. We've been using them. It's just now time to formally define what they mean. Okay, just a relationship between things. So here's an example for you to try now. Take this relation. It's a relation on the same set, so it's mapping the set 1, 2, 3, 4 to the set 1, 2, 3, 4. Those, they're related to themselves. Same set's related to itself. And see if you can give a matrix representation of it, and then also give the relation as a set of ordered pairs, saying what's related to what. Okay? And so the first thing, using this notation, the first thing that's related, the thing on the left is where the arrow is coming from, and then where the arrow is going to be the thing on the right of the relation, because the order is important. Just like for this one, I can relate x's and y's where x's are integers, but y's are forced to be real numbers instead. Okay, so the order really matters, and I think you can see that. Like, the order really matters for less than. It's not true that 3 is related to 2, but 2 is totally related to 3 under the less than relation. Okay, so that's why we have to draw arrows. Yeah, so here is, like, let's pretend this is a binary relation on the set A, and A is equal to 1, 2, 3, 4. That's the domain of the relation. Okay, so give it as a matrix and give it as a set of ordered pairs. Looks like it wants the matrix first, so who am I to do it differently than that? So it doesn't matter which one we draw first. 1, 2, 3, 4 is going to be related to 1, 2, 3, 4. And it's always the thing on the left is from the row, and the thing on the right is from the columns. Okay, so for example, 1 is related to 1, so I'm putting a 1 there. Okay, there's only one way for that to happen. And then 2 on the left is related to 1 on the right, because it's the target of the arrow. 2 here, 1 here. There's a 1. And then, okay, what about this arrow? That's 1 is related to 4, so 1 and 4. There's a 1 there. 3 is related to 3. Boop, boop, boop. There's a 1 there. And then I think this is the last one, I hope. 4 is related to 3. So 4 is related to 3 in this order. So 1 there. So I think, is that correct? 3, oh, I think I missed this one. 3 is related to 2. So 3 and 2. I put a 1 there, and now this guy looks way out of place. 3 is related to 3. Let's move him up. That looks better. Okay, so that is all the 1s in the relation. That's all the things that are related. Everything else is then a 0. Whee! And so you could read off the answer as from the order pairs from the matrix or from the diagram. It doesn't matter. So here's the relation. Let's call it R. Well, what is related to what? 1 is related to 1. Here you just give the things that are related. Everything else is assumed to be not related. And then 1 is related to 4. Let's try and do this systematically. Is 2 related to anything? No. Is 3 related to things? Yes. 3 is related to itself and to 2. Okay, what about 4? 4 is related to 3. That seems to be it. Did I miss anybody? 1, 1, 1, 4, then, oh, I missed 2, 1, sorry. Let's try and keep this in order. 2, 1, there, comma. And so that is my relation. There's 1, 2, 3, 4, 5, 6 arrows, so there should be 6 things in my relation. And it looks like there is. All right, did you get the matrix and the set of ordered pairs? Remember that the order is very important. It's always the thing on the left and the thing on the right. You cannot swap these usually. Okay? Sometimes you can, though, and there's a word for that. There are plenty of words for other things, too. So let's talk about all of them, because these are very important properties for relations to have. So a relation on a single set, let's pretend that it's called R and it's on set A, it can be any of these things, and these are nice things to have a lot of the time. So I promise to give more examples, but look at the dogs for right now. You can have your relation R, it can be reflexive, we say, if every element is related to itself. That is a reflexive relation. We'll talk about some examples of those. The opposite of that is anti-reflexive. If for every element in A, it's never true that X is related to X. So you can express this fact by drawing like a slash through the symbol a lot of the time. So X is not related to X, no matter what. You can have symmetric relations. Like if you have two things, it is a symmetric relation, R is a symmetric relation, if whenever you have X related to Y, you also have Y related to X. If and only if. It's always the case that both of these pan out. They are always related to one another. So like 1 and 2, if that's in the relation, if 1 is related to 2, then 2 must also be related to 1. Notice that this is not true for some relations. Some relations are not symmetric, like less than. It doesn't work out, right? 1 is related to 2, but 2 is not related to 1. So that's not a symmetric relation. Perhaps it's anti-symmetric. This one isn't. But a relation is anti-symmetric if you have both of them. If you know that X is related to Y and Y is related to X, then the only way that could have happened is if X is equal to Y. So if you have both of these, if X is related to Y and Y is related to X, then that implies that X is equal to Y. So you can have an anti-symmetric relation. A good example of that is like a less than or equal to relation. I'll give you more, if not that one again, in a second. And then finally, you can have a transitive relation. That's also nice to have a lot. And this involves 3 separate elements. So if this is true, then a relation is transitive. If for your 3 elements, if you know that X is related to Y and Y is related to Z, then it must always be the case that X itself was related to Z. So these guys match up if these align. Okay? That's the idea. So like if you know that 1 is related to 2 and 2 is related to 3, then that implies that 1 must also be related to 3 under your relation. Okay? And certain relations are like this. Less than works for this, right? If you know that 1 is less than 2 and 2 is less than 3, then that automatically means that 1 is less than 3. Okay? So I went through that kind of quickly. Let me give you some more real examples of all this stuff. Okay? Let's give it all a try. So let's talk about reflexivity first and anti-reflexivity. So reflexivity means that every element is related to itself. So I don't care what the set is, it's A. You might have some other things true about A, like some things might be related to other things too. It's not a problem. But you know, if it is related, if it's a reflexive relation, whatever you have, if R is a reflexive relation on A, then you know you must have these self-loops for every element. Reflexivity means that every element is related to itself. Okay? So there are a lot of nice reflexive relations. We know that less than or equal to is a reflexive relation, right? Every number is always less than or equal to itself. Equality is, of course, a reflexive relation. It's only ever the case that a number is equal to itself, right? So that reflexivity comes up a lot in the wild. Anti-reflexivity is kind of the opposite, and it's also very common. It means that no element is related to itself. So your strict less than and greater than operators are prime examples of anti-reflexive relations, because it's never true that 2 is strictly less than 2. Not true. Right? 4 is never greater than 4. Not strictly. Okay? So these are anti-reflexive relations, where like less than or equal to is a reflexive relation, because it has that equal to part. That means that things can be related to themselves. Okay, so that's reflexivity. Hopefully that makes a lot more sense now. Let's talk about symmetricity. All right, so you can have a symmetric relation, and that, remember, means that you can swap things. You know that if you have X related to Y, then you also have Y related to X. Okay? It kind of means that you can swap the elements. The order of the elements in the relationship doesn't matter. Okay? So you don't have to draw arrows anymore. You can just draw lines, which is interesting to think about. So here is, maybe I'll go back to blue. Here's an example of a symmetric relation. Here's my set A, and here are some elements of A, and let's say that this is my relation. Like, I know I have all these things. And so, if it's a symmetric relation, then you know immediately, once you have this arrow, you also have this one. Once you have this arrow, you also have this one. These elements are related backwards. These elements are related like this, too. Okay? You always have the other arrow. So you can just draw a line instead, usually. So there are plenty of nice symmetric relations, right? So equality is a nice symmetric relation, because if you know that, like you're doing algebra, x is equal to 2 is the same thing as saying 2 is equal to x, right? Makes no difference. It's a symmetric relation. Obviously, x must be 2, but that's beside the point. It is a symmetric relation. Okay? Is related to is also a symmetric relation. So I'm related to my sister, and my sister's also related to me. It goes both ways. Does that make sense? So that is symmetric relations. Those come up a lot. Let's talk about anti-symmetric relations. That means that you cannot have both. Going back to the definition up here. If you have both of these, if you know that one thing is related to the other and that other thing is related to the first thing, if you have both, that means that those things were really just equal. You didn't really have things being actually symmetric, different things being actually symmetric. Okay, so that's what anti-symmetric means. So here are some relations that are anti-symmetric. It means you can't have both x are y and y are x when x is not equal to y. Okay, it's only ever like this one is true or this one is true. Otherwise, they're equal. Okay. So strictly less than is an anti-symmetric relation, okay? Because 2 is less than or equal to 3 if and only if, right? You cannot have 3 being less than 2. It better be the case that this is not true, all right? Because that implies this. You see that? So that is an example of an anti-symmetric relation. You can't have both. Is older than is also an anti-symmetric relation. So, for example, I'm a brother, I'm older than my sister, like I'm 29, my sister's 27, and so this is true, like brother is under the relation is older than, so this is a true statement, but you can't swap them, okay? It's technically less than all over again, isn't it? Or this is like greater than, kind of. So that is another anti-symmetric relation that comes up in real life. All right, so that is symmetricity, anti-symmetricity. Let's talk about transitivity, because once we have all of these, like a trifecta emerges. Like you can have reflexivity, symmetricity, transitivity, and that just makes for a very nice relation. And we'll get into that soon. Okay, so transitive relations are like this. They let you like take two things and line them up. Okay? You can line up two relationships and get a third out of the deal. Okay? So for example, if you have and you know that x is related to y and y is related to z, then transitivity tells you that, like if these align, then you also have x related to z. You also get that out of the deal. Okay? So a ton of relations are transitive that we already know about. All of these are transitive. Less than, equal to, greater than, equal to, all of them are transitive. It's saying that if you know this, like 2 is less than 3, and you know this, like 3 is less than 5, because it's a transitive relation, if you have things that align in this way, you immediately know that 2 is related to 5 under that relation. You can conclude that 2 is less than 5 as well. You see how that's a true statement? See how that works for all of these? That is true. Okay? Same with is related to. Like, I'm related to my sister who's related to my cousin. That means I am related to my cousin. Yes, I can conclude that immediately. Sadly, is in love with is not a transitive relation all the time, right? So that's quite nice. So yeah, this is what transitivity means. If I have my set A, here it is. Fun to think about. Here is, like, if I know I have these two things, transitivity means, if I know that this relation is transitive, it means that I can conclude this in this direction. See that? I can, like, go both at once. I can always draw that arrow and get there immediately. Go straight to that element. Okay? So hopefully that makes enough sense. That is transitivity. Some nice thing that I want to show you right now before we go any further and I give you something to try yourself. Let's check and see where we are. What I'd like to do is just give you a little aside. If you have symmetricity and transitivity, if you know that your relation is symmetric and transitive, a lot of the time you essentially get reflexivity too out of the deal, which is really weird. I'll call it pseudo, because some other things have to be true for you to get true reflexivity. But here's the idea: pseudo reflexivity comes out of it. So like you don't even have to know that the relation was reflexive, but once you have symmetricity and transitivity, you might be able to get out reflexivity. Let me show you this. So if you know your relation is symmetric, that means the second you have this, you must then add this, right? That is symmetric, the definition. If you know your relation is also transitive, look what happens. That means that, okay, this is related to this, cool, and that middle thing is related to that thing. That means, oh man, I don't have to make this big loop between two things. I can go straight like that. See how you got a reflexive relation out of it? Same with this one. If I can go here and here, that means I can stay here. This is related to this. This is related to this, which means the first thing is related to itself. Crazy, huh? So that gives you essentially reflexivity if you know you have all of this. And you have arrows between everybody, at least one arrow between people. That gives you reflexivity. The reason I don't call it true reflexivity is because you can have this, like you can have somebody laying out in the set that is not related to anything, and you do not get reflexivity for it. You see that? It has to be related to somebody else for this to all kick in and give you reflexivity for that element. But for everybody who is related to somebody else at least, then symmetricity plus transitivity essentially makes it so that those particular elements are reflexive. They're related to themselves. Okay, so that was just a fun thought. I want you to try this now yourself. So here are a bunch of relations. I think I got this way off. We're going to keep going, definitely. So here are a bunch of relations, and I want you to think about whether each of them are reflexive, anti-reflexive, or neither, symmetric, anti-symmetric, or neither, and transitive, or not transitive. Okay? So give this a try, and then we'll come back and talk about them. So, let's see what we're doing here. So the first one is this relation. We'll call it T. It's relating a group of people, okay? So X is related to Y under T if Y is taller than X. So maybe it's it's essentially a less than relationship on the height of those people. So there are at least two people in the group who are not the same height. That might be useful in a second. What is it? Is it reflexive, anti-reflexive, or neither? Symmetric, anti-symmetric, or neither? Transitive or not transitive? So pick something from here, and something from here. Okay? Let's talk about this. So is this a reflexive relation? Is a person taller than themselves? That is never true, right? That is never true. So this is immediately an anti-reflexive relation. Does that make sense? I hope so. And then, okay, let's go to symmetric. Is it symmetric, anti-symmetric, or neither? Is it the case that if you know like that person A is taller than person B, does that imply that person B was also taller than person A? No, that's actually never true, right? Again, that's never true. So that is anti-symmetric. Yeah? All right, final one. Is it transitive or not transitive? If you know that person A is taller than person B, and you know that person B is taller than person C, does that give you that person A is taller than person C? I think so, because it's that less than relationship all over again, and that is totally a transitive relation. So it looks like that this relation T is anti-reflexive, anti-symmetric, and transitive. Okay? So that's that. And let's continue and try this for B now. What'd you get for this one? So this is a binary relation on the set Z, all of the integers, and it's defined to be this. So AB, oh, sorry, it's a relation on the pairs of integers, excuse me. Pairs of integers related to other pairs of integers. So A comma B, that pair is related to C comma D if this is true, like A is the first elements are less than or equal to themselves, and then the second elements are also less than or equal to themselves. So A is less than C and B is less than D. That means that these two elements are related in that order, okay? So let's see what that means. Is this a reflexive relation or anti-reflexive or neither? So what does this mean? Is it true that AA is related to AA? So let's check the definition. Is A less than or equal to A? Yes. Is A also less than or equal to A? Yes. So this is a reflexive relation. That's good. All right, let's try symmetric. Is, if I know that, let's see, should I maybe do an example here? If I know that A and B is related to C and D, does that give me that, question mark, that CD is related to AB? So this is true. If this is true, that means that A was less than or equal to C and B is less than or equal to D. And then for this to be true, it would have to be the case that C is less than or equal to A and then D is less than or equal to B as well. These can never both be true, right? Same with the others. Those relationships can never hold unless B is equal to D, right? These relationships cannot hold unless A is equal to C. And that is the textbook definition of anti-symmetric. See that? All right, finally, let's try transitivity, and I've run out of room down there, so let me write up here. So if I know that I have two elements related to each other, let's do like, I don't know, let's try and hard code them. Let's be like, okay, 2, 3, I know that 2, 3 is related to 3, 3, for example, because this is less than or equal to 3, 3 is also less than or equal to 3, and then if I also have 3, 3 related to 4, 5, this is again true because 3 is less than or equal to 4 and 3 is less than or equal to 5. Do I immediately get that, if I draw it this way, do I immediately get that 2, 3 is related to 4, 5? Is it automatically the case that 2 is less than or equal to 4 and 3 is less than or equal to 5? Do they line up like that? Always? And the answer is yes. So this is a transitive relation. You'd have to be more thorough though. Like this is just one example. You have to prove it more thoroughly like I did down here. But I think we can extrapolate pretty easily to understand that this is totally a transitive relation. Yeah? So that's going on there. And yeah, I didn't know like how much time this would take, so disregard this. Let's just keep on trucking and see how much we can do in the amount of time we have left. All right, so what I'd like to talk about next is directed graphs. So let's get into those. What in the world is a directed graph? Short for digraph. Or digraph is the short form of that. So that is a pair of things, VE, vertices and edges. It's essentially like how we're mathematically specifying pictures like this. We have some nodes, also called vertices. So all these things like places, for example, those can be my vertices. And then I can have relationships between those vertices, like maybe roads to get there, right? So, for example, I can have San Jose related to San Francisco. I can have Fresno related to San Jose, right? Does that make sense? In order to get to LA, I have two options. I can take these paths or these paths. And that kind of diagram is called a directed graph, okay? Because arrows have directions, like say we're going from Fresno always, we're starting there, now we're trying to get somewhere, okay? This is called a directed graph. It's a pair of things, v comma e, vertices and edges. Okay, so v is the set of vertices, so v is all the cities, let's say, and edges are the things that connect the vertices. It is a subset of v cross v. It's a relationship between vertices. Each edge is a relationship. So like Fresno is related to San Jose, it's an edge. You can get there from there. Okay, you can also go to SLO from Fresno. There is an arrow in that direction. Okay, it's related in this way. Notice that there is not also this. Let's pretend that there is not also this. Like the road's closed in the other direction for some reason. This is a directed graph, so the arrows have direction. Okay, and so the edges are just like, okay, there's an edge between Fresno and SLO. There's an edge between Fresno and LA, so on and so forth. Okay, so digraphs, short for directed graphs, those represent a lot of cool stuff, like relations, of course. You can draw them out like this as a directed graph. We've been doing that this whole time. I just haven't told you what it's called. You can have it represent maps, like Google Maps. Technically, when it's trying to find directions for you, it's making a digraph of all the different roads and how they're connected to try and find you the fastest way to get around. It's a very common thing. And yeah, there's usually a concept of like moving around. Like you'd want to go somewhere, kind of. Like, so maps are a good example of a digraph. You want to move around. You want to go from Fresno to San Francisco. You want to go from Fresno to Santa Barbara. Things like that. Okay? And when you move around, you're following the valid directed edges to get to places, okay? And when you chain a bunch of these edges, you end up with a path to somewhere. That's the fancy term. It's really just called a path. So like there's a path from Fresno to Santa Barbara. There are two paths from Fresno to LA. One's like that, and one's much shorter, okay? A single edge counts like technically as a path as well. Okay, so that is directed graphs in a nutshell. And that is going to be useful in just a bit. Okay, let's also talk about, we had function composition. I would be doing you a disservice if we didn't talk about relation composition, because relations are very similar to functions, just they have a lot less strict of rules, right? So let's talk about how to compose two relations, R and S, okay? So it's very easy when both relations are on the same set. That works out just fine. It makes a third relation on that same set and use the same notation, S after R. Okay? So here is the composition relation. You know that A is related to C under the composition relation if, and only if, you have A related to B under R, so you do that one first, because it's right here, it's S after R still, right? And then you have B related to C in S. So if A is related to B in R and B is related to C in S, then A is related to C in their composition. So here's kind of the idea. So if A is related to B, here's A and B, here's R, and B is related to C. B is related to C under the relation S, then we know that A is related to C under S after R. So do R first, then S. Anywhere you can get there in that order, you have an arrow. Okay, so that's the composition of those two relations. Hopefully that makes sense. So, yeah, you work right to left just like you do for functions. It's the same kind of concept. First do R, then do S. And let me give you an example, because it looks a bit different than a function. Like, we're not applying things anymore. It gets a bit weird. So let's talk about that. Here's my set, A, B, C, D. And let me draw you these relations, A, B, C, D. So let me use, for the relation S, let me use blue. And then for the relation R, I will use green. Okay, so let's draw the relation S first. So A is related to B under S, so blue. A is related to C under S. C is related to D under S. And C is related to A under S. Okay, then under R, we have B related to C. We have C related to B. Other direction. A is related to D, and D is related to B. Okay, so those are my two relations, and now let's talk about what the composition S after R is. What must that be? I guess I can draw that in rainbow. Let me draw a mini version of the same set down here, because I need a lot more space. So here's A, B, C, D again. And let's try and figure out what this has to be. So is, like, for example, is A related to B under the composition? So first do something in R. There's nothing. First do something in R. So like, I don't know, this. That gets me to C. And then do something in... oh, sorry, not in R. R is green, isn't it? So first do something in R, like this, and then do something in S to get to B. Oh man, there's nothing there. So A is not related to B under this relationship. First do something in R, so do something green, and then do something blue. Does that make sense? That is the composition. And this large circle is bothering me, so let me redraw it. All right, so with that in mind, it's not too bad to figure out the composition. So first I do a green thing, then I must do a blue thing. So with this one, I'm here. Is there any blue things to do? No, so there's nothing composed. A is not on the left side of anything. Okay, alternatively, let's start at B. I can do a green thing. Can I do a blue thing now? I can do two blue things. So B is related to, under the compose relationship, I can either go up to A or over to D. So B is related to both A and D. Because I can do boop boop. B is related to A. And I can do boop boop. B is related to D. You see that? That's how composition works. All right, so I just covered this green one. We already did that one. Let's do this one. C, starting at C, do a green thing, do a blue thing. No blue things to do. Darn. Finally, for this one. Do this, now do a blue thing. Oh, there are no blue things. Darn. So it looks like this is S composed with R. That's all the things you can do in order. And you ended up with a smaller relation than either of the two. That's totally fine. So under the compose relation, S after R, it looks like B is related to D and B is related to A. And that tells us useful information, okay? So, yeah. The way to figure this out, to do it fast, is if you want to compose a relation, you find paths of length 2, one from the first relation and the next one from the second relation, okay? Working from right to left, of course. If you're composing a relation with itself, that just means find all length 2 paths. Like, pretend that this is all blue, for example. Like, go here and then here, things like that. It always will work. Just compose means put some arrows after each other if it's the same relation that you're composing with itself. Just find all the length 2 paths that exist, which is kind of cool. Let's see if we have time for closure, and that should maybe do it. So yeah, maybe let's try these 2 slides. Let's get those in, and that'll be it for the day. Whee. That's the plan, at least. So sometimes we have relations, and unfortunately that relation is not reflexive, it's not symmetric, it's not transitive, or some combination of those. But we really like those terms. We really like when our relations are reflexive, symmetric, or transitive. If we want to make a relation, we want to take our relation R and make it reflexive. We want to take it and make it symmetric, make it transitive. You can do that. The idea is we want to make the next bigger relation, like the smallest relation that is the same as R, but also the thing that we wanted. Also reflexive, also symmetric. We don't want to add extra stuff, just enough stuff to make it what we want, just to make it symmetric, just to make it transitive. That doesn't mean make everything related to everything else. Just add the fewest number of arrows and make it symmetric, make it reflexive, make it transitive. Okay? So the idea is, it's called the closure. So if I want to modify R to be reflexive, for example, then I make the reflexive closure. That's what it's called. If I want it to make it symmetric, then I call it the symmetric closure. So just fill that in with anything. And here's how you do it. Here's how to make that next how to add the fewest arrows to make it reflexive, symmetric, and transitive. So if you want to make your relationship reflexive, just make everything related to itself. Add xrx for every x. Does that make sense? So for example, the reflexive closure of strictly less than is less than or equal to. Does that make sense? That's not too bad, right? So just add xrx. That forces you to do stuff. Symmetric closure. That just means if you have xry, add an arrow in the other direction. Make yrx. You're forced to have that. That's what it means to make the symmetric closure. Those are the arrows you have to add. Then finally, for transitive closure, just notice if you have xry and yrz, you must add xrz. Keep doing that until there's nothing left to add. That might end up giving you some reflexivity, right? Remember all that? So, excuse me. Yeah. In terms of graphs, it's quite easy to do all this. It just, if you want to make it transitive, if you can find a path from x to y, regardless of how big it is, because of this, the way this is going to work out, then if you can find a path from x to y in the relations graph, add xry to the relation. Okay? So this will make more sense with an example. Here are some closure examples. All right? Let's try doing the reflexive closure of this relation. That one's the easiest, right? It's just always add xrx for every x in the domain. So here, everything must now be related to itself if it wasn't already. Does that make sense? That's easy. That's making the reflexive closure of the relation. And all these original arrows, they still exist. We're building a bigger relation that is also reflexive. Okay? That's that one. Let's do symmetric closure of the same relation. So that means if I have this arrow, I better add the other direction. Boop, 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 and boop. That's the symmetric closure. Does that make sense? That means if you have xry, you must add yrx. Bam. And then finally, transitive closure. That one requires the most work because you might add one arrow and then have to add more based on that new arrow. So that means if you have xry and yrz, then you must add xrz. Hopefully I didn't just mess this up because I need room to potentially draw an arrow right there. There. Okay, so that means like for this one, I have this one and this one. That means I'm forced to add this. See that? And now, oh man, I have this one and this one. See how you might have to add even more things? Now I'm forced to add this one to go straight here. Just if you have a path anywhere at all. Like bam, 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 eventually I'm going to have to add this one. That's what I meant by saying this. Okay. Let's fill in the remaining pieces now. So again, the reason why I could do this was, okay, I had these two, which is going to give me this one, and then I had these two, which gave me this one, and then now suddenly I have, let's see, what's a good way to get there? I now had, I guess it was just this one and this one that always gave me that one. That makes sense. What else? What am I missing? Well, if there's a way to get here to here, then I can go straight here. Same with all that. Does that make sense? Let's see, are there anything else? This one and this one is going to give me this, which is then going to give me this one and this one to give me this. Now there's a path, right? Just follow all the paths. Add an arrow if it's not already there. Let's do it like that. And then 1 to 3, right? I already added that one. Just 1 to 5. It's already there. 1 to 4. So 1 can go everywhere right now. You see that? That's interesting to think about. 2 can't go back to 1, but it can go to 5, to 4, to 3. 5 can go... can it go back to 2? No, it doesn't look like it. But it can go to 4, which means it can also go to 3. Bam! Because of these two. See how transitive closure kind of makes you add a bunch of stuff? There's a lot going on here. Let's see. Hopefully I didn't draw any extra arrows. Sorry if I did. 4 already going straight to 3. It can't go back to anybody though. And then 3 is the target of everybody. It's not going anywhere itself. So I think, in theory, this is the transitive closure of this relation. Let me just check my notes, make sure it's all working. But yeah, notice how the second you add something, you might have to add more things based on that arrow. It's really just, if you can find a path, like 1, 5, 4, 3, you know that eventually, given transitivity, you're going to add 1 to 3. Hopefully you see that now with the example. Okay, so that is my examples of closure. That's where I want to stop for now. But before we go, I want to just highlight something that I'd like you to do. This is week 8. It's the middle of the semester. So what I'd like you to try, please, this is not for any credit or anything, it's just for me, try and fill out, if you have some time, this mid-semester anonymous feedback link. You'll go here, click the link, and take the survey. You can answer as many questions or as few questions as you want. This is just for me as an instructor. It's completely anonymous. Doesn't count for anything at all, but it would help me to improve the class while you're still in it. So please consider doing this, and that is all that I have for you. I don't think I'm releasing any new labs, so this is the last video for this week, and I will see you in the next week. We'll talk more about closure.